We're going to pick up with problem number 23. Let me fix my camera. So let's go look at problem 23. Sketch the graph of the following function. Indicate where the function is increasing or decreasing, where any relative extrema occur, where the asymptotes, the graph is concave up or concave down, where any points of inflection occur, where any intercepts occur. So basically, what we're doing now is we're doing everything you learned from both the first and the second derivatives, along with asymptotes. So I think what I'll do is just write down this function, and we'll go and we'll try and do about everything we can with this function. And then we'll go back and try and answer the questions, and hopefully we will be able to answer all the questions based upon what we've done. So once again, especially in terms of graphing, in your mind, if it helps to do some of this, you can always think of this. You can always replace f of x with y. Ultimately, we're going to try and graph this function, but we're going to learn all kinds of things about it. Now, I don't think it's going to be asked here, but one of the first things that sometimes people ask about are intercepts. You have both X-intercepts and Y-intercepts. Hopefully you remember from algebra, the way you calculate the X-intercept is you take the equation and set y equal to 0 and solve the equation. Well, if I set y equal to 0, then I say what value of x would cause this whole thing to be 0? Actually, there are no X-intercepts, which means when we get ready to graph this, this graph is never going to touch or cross the y-axis, or the x-axis, sorry, the x-axis. It's never going to cross or touch the x-axis. How do we calculate the y-intercept? Well, you set x equal to 0. Now, if we set x equal to 0 here, we have minus 3 over 0 minus 7, 3/7. So really our y-intercept is like 0, 3/7. We don't need this point here, but it's just interesting when you're ready to graph it. That helps. Now let's look at asymptotes. We definitely are going to need to know the asymptotes. Let's do vertical first. Right, vertical asymptotes. Remember, the whole key is set the denominator equal to 0. There's our vertical asymptote. Now, if I wanted to start graphing this, as I'm learning these things, now the good thing is, since this is an online assignment, I assume when they get to the graph, it'll be multiple choice, but just as part of our working through this, let's go and do it ourselves just to help understand it. So there is a vertical asymptote, one vertical asymptote. Horizontal asymptote, you remember, reduced to leading terms. You have minus 3 over x. If x gets really large, this thing approaches 0. So we have a horizontal asymptote of y equals 0, basically your x-axis. So what this means is when we figure out how to graph this equation or this function, sort of like it's broken up into 4 separate squares. So there's probably going to be a couple graphs somewhere in these squares here. So let's go ahead and now look at the first derivative. Remember, the first derivative will give us any maxes or mins, and we can figure out increasing or decreasing. So first derivative. Now, I'm looking at my function. I could use quotient rule, or I could move this to the top and sort of use like a chain rule concept, which I think I'm going to do. Let's just call this so if I take the derivative, it's minus 3 minus 1 x to the minus 7 to the minus 2. Basically 3 over x to the minus 7th squared. Now to find the critical points, you set that equal to 0. And then you ask what value of x, you solve this. There's actually no solution. So there's actually no critical points, no maxes or mins. All right, that happens sometimes. However, since there is a vertical asymptote, we can think of the vertical asymptote as breaking this up into regions. What I mean by that is, if I draw a little chart here, and I look at x equals 7, it's like I have 2 regions here. In each of these regions, the first derivative is not going to change. It's either positive or negative, which means these regions, either the function is increasing or decreasing. I don't know which. Let's figure out which. Let's plug in 0 into my first derivative, which is right here. If I plug in 0, I see that this ends up being a positive number. So actually, this is an increasing region, right? If I plug in, say, 8 into here, it's also positive. So actually, both these regions are increasing. I think they're going to ask me that. So increasing are the intervals negative infinity to 7 and 7 to infinity. Let's see what the second derivative teaches us. So if the first derivative, I'm going to write it like this. Second derivative would be 3 times minus 2 x minus 7 to the minus 3rd, which is really negative 6 over x minus 7 cubed. Now to find points of inflection, I set this equal to 0. Once again, no points of inflection. However, concave up and concave down, I can go here and see what's happening on either side of 7. If I plug in 0 into my second derivative, this denominator is negative, and a negative turns out it's positive. Concave up. If I go look at 8, positive, negative, negative, concave down. So concave up is going to be from negative infinity to 7. Concave down is going to be 7 to infinity. Now my guess is what's going to happen is here's my guess. When we graph it, it's probably going to look like this. Concave up, concave down, increasing, increasing. No maxes or mins, no points of inflection. Let me go start answering the questions and see if I've got everything I need. So the first question, function increasing, decreasing. We said increasing 2 intervals. So I got to look for the one increasing and never decreasing. And it's increasing from negative infinity to 7. And then also from 7 to infinity. Relative extrema, maxes and mins. We found out there are none. Vertical asymptotes. We said there's x equals 7, one vertical asymptote. Remember, type it as an equation. Horizontal asymptote. We said y equals 0. Once again, typed in as an equation. Slant or oblique asymptote, there aren't any. Concave up and concave down. We decided concave up, negative infinity to 7. So I'm going to choose A here, which has a concave up and a concave down. The concave up part is negative infinity to 7. And concave down 7 to infinity. Points of inflection, we said there are none. Oh, it did X-Intercept. I'm glad we did these. X-Intercept, we said there aren't any X-Intercepts. Y-Intercept, type an ordered pair. We said 0.375. And the graph, here's the asymptote, x equals 7. The one we drew looks like C. All right. That was a lot of work, but we were able to figure it out. 24, I think, is the same kind of problem, just a different function. So let's write down the function, and then we'll do the same kind of thing that we just did. So this is 24 f of x equals 3x minus 2 over x. All right, so let's just try and figure everything out. Let's do intercepts first. X-intercept, so you set y equal to 0. Multiplied both sides by x, and you get 0 equals 3x minus 2. If you solve for x, I believe you get 2/3, which means the actual x-intercept as a point is 2/3 0. Y-intercept, you set the x is equal to 0, and you can see right away I would be putting a 0 in the denominator, which I cannot do. So right away, I know there are no y-intercepts. How about vertical asymptotes? Look at this denominator. What value of x would cause the denominator to be 0? Once again, vertical asymptotes. I don't even care about the numerator. I sort of ignore it. All I care about is the denominator. Horizontal asymptote. If I reduce down to leading terms, the x's cancel out. Looks like I'm going to have a horizontal asymptote of y equals 3. If I go down to the very bottom, if I try and sketch in some of the stuff I'm learning, we'll see if we can come up with an edit of the graph. First of all, x-intercept 2/3 0. Maybe right about here. I have vertical asymptote x equals 0. Horizontal asymptote y equals 3. All right. Now let's start looking at the derivatives. First derivative gives us maxes and mins and increasing and decreasing. Let's do, actually, let's simplify this. I could use quotient rule. But if I split this up into two fractions, right? This original function, I could actually write it like this. So therefore, first derivative of 3 is 0. And this is going to be -1 times -2, 2 x to the -2, 2 over x squared. Find the critical points, set that equal to 0. It's interesting. Once again, no critical points. There's not going to be any maxes or mins. However, I will have regions I can look at, because when x is 0, because I have an asymptote there, the asymptote breaks it up into two regions. So let's take -1, plug it into my first derivative, and see what my sign is. Well, since it's squared, it's going to be positive, which means it's increasing. If I plug in 1, it's also positive. So both these regions are increasing. So once again, I have two increasing regions. Negative infinity to 0 and 0 to infinity. Second derivative information. So let's say the first derivative will start out with 2x to the negative 2. Second derivative, two times negative 2 x to the negative 3 negative 4 over x cubed. So if they set that equal to 0 to find your points of inflection, it looks like there's no. But once again, I might have regions of concavity. If I look at where this is undefined, it breaks it up into two regions once again. If I plug in negative 1 into my second derivative, this bottom becomes negative. Two negatives make a positive. So concave up. If I plug in 1, it's negative. Concave down. So up is negative infinity to 0. Down is 0 to infinity. So what might this graph look like? Well, I know here, I know in this region, it's increasing and concave down. Should be more like a curve here. And normally these things are like catty corner. So my guess is probably something like this. Let me go see if I can answer all the questions and see how we're doing. Increasing, decreasing. I had two increasing regions, so increasing only. Negative infinity to 0, and then 0 to infinity. Maxes or mins, relative extrema. Once again, there aren't any. Vertical asymptotes, I said x equals 0. Horizontal asymptote, y equals 3. There are no slant or oblique asymptotes. Concave up, concave down. I have one concave up, one concave down. So concave up, negative infinity to 0. Concave down, 0 to infinity. There were no points of inflection. X-intercept, 2/3 0. Y-intercept, there weren't any. And the graph. This is the one that looks like ours that we created. All right, looks like we have one more of these at least. Let's just keep going now. Pretty much going to follow the same procedure. All right, sorry. I did drink a little bit there. Let me write down this function for 25. F of x equals x plus 2 over x squared minus 3x minus 10. And all the normal stuff. All right, we pretty much know the routine now. X-intercept. One shortcut for x-intercept, you have a fraction. You sort of ignore the denominator to get the x-intercept. You can just set the numerator equal to 0. That's like a little shortcut. So I have an x-intercept of -2, which means there's my x-intercept. Y-intercept is where you set x is equal to 0. You knew that, you get 2 over -10, -1/5. There's your x-intercept and your y-intercept. Oh, vertical asymptote. Set the denominator equal to 0. This factors into x minus 5 times x plus 2. So when you solve that, you get -2 and 5. So there are two critical points. Oh, sorry, misspoke. Two asymptotes. If I go way down and start thinking about a graph, here's x equals -2. X equals 5. Horizontal asymptote. You just look at the leading terms. X over x squared, which is 1 over x. What happens to this is x gets very large. Approximately equals 0. So y equals 0 is your horizontal asymptote. Basically the x-axis. All right. Let's look at the derivatives. Definitely going to use quotient rule. So low d high, low is x squared minus 3x minus 10. Derivative of what's on top is just 1 minus high d low. Derivative of the denominator is 2x minus 3. all of that over, whoops, the denominator squared. Very messy. And the one good thing is for the critical points, you set this whole thing equal to 0. And once again, you sort of ignore the denominator. The solution is going to be when the numerator equals 0. Let's go ahead and multiply all this out. So I have x squared minus 3x minus 10. Here I have these two binomials. X squared minus 3x plus 4x minus 6. Whoops. Hang on. X times 2x, well, should be 2x squared. X times 2x, x times negative 3, 2 times 2x. Wow. All right, glad I got that. Actually, these combine into just x. So now x squared minus 2x squared, negative 3x minus x, and then negative 10 minus a negative 6, negative 10 plus 6. So there is your first derivative. Now to find the critical points, I set that equal to 0. And I can make everything positive. Multiply both sides by negative 1. This actually factors. Looks like there's your critical point. Now, when I look at the regions for this, I have to look at both the critical point and my vertical asymptotes. Sort of interesting, one of my asymptotes is the same as a critical point. And that happens sometimes. Sometimes asymptotes get touched or crossed. We'll see what happens here. So let's look at the regions for the first derivative. Got negative 2 and 5. Looks like 3 regions. So region 1, if I pick like negative 3, oh, see, the first derivative is sort of messy because it's this whole thing. So really, let me try. I got to keep track of this. This is where it could get messy. Here's the numerator. And here's the denominator. Oh, but that's, these are both squared. Now we do have some canceling that goes on here. This is getting very complicated. Oh, they actually, this and this is the same. So actually, the first derivative reduces down to this. So we'll see what this looks like. This one's pretty complicated, but anyways, I'm going to assume the 3 regions here. Even if there's not quite 3 regions, there's nothing's going to be harmed. So if I plug in like -3 here, this thing's going to be negative. If I plug in 0, it's negative. Matter of fact, all these regions are negative because you got something squared in the denominator, which always makes it positive. So it's interesting. I think this might be a neither, or it just might be a, it goes like this. We'll have to see. Now the second derivative, so if this is the first derivative, or I could rewrite it. Second derivative would be 2 and I think there's going to be 2 regions of concavity. Region 1, if I plug in 0, this is negative. If I plug in something like 6, this is positive. Points of inflection, I don't think there's any points of inflection. All right, let's start plugging stuff in. This is pretty messy. I could have made some mistakes. Try and figure out, I'm not even gonna try and graph it. We'll just look at the graph, the answer, and figure out what looks correct. Increasing, decreasing. So I'm going to say increasing. I think I've actually 3 regions of decreasing. From -8 to -2. And then from -2 to 5. And from 5 to infinity. Now, to be honest, I'm not 100% sure about this. Hope it's correct. All right, that's good. Relative extrema. That's where the first derivative is 0. I think we have one of those neithers. The coordinates. I know x is -2. So I got to go figure out what the value of the function is. But I put in -2. You get undefined. So I think the function is undefined. It's interesting. So my guess is maybe there are none. All right. For lower class asymptotes, these are pretty straightforward. X equals -2, x equals 5. That's 2. The leftmost equals -2. The rightmost, x equals 5. Oops. I wonder if this x minus 2 is like a whole, because the bottom and the top are both the same. I bet it's not an asymptote. It's probably like a whole. So my guess is there's just one. So if you go back to algebra, the concept of a whole is where you have the same parenthesis in the top and the bottom. I forgot to check for that. I think that's what's going on here. We'll just try and answer these questions and see what happens. Horizontal asymptote, I believe, is correct at y equals 0. Now there's no oblique asymptotes. Concave up, concave down. I think, and this is probably correct, concave down from negative infinity to 5. And concave up from 5 to infinity. All right, so this is where let me just check. First thing is, let me check and make sure. Let me go back. I'm going to sort of show you what I'm going to play with for a minute. I want to spend a lot of time on this. This thing actually, if we factored it from the start, would be so this is a little tricky because you can sort of think of this as the original function. So when we took the first derivative, it ended up being then if we took the second derivative, it ended up being so if you think about this as a second derivative, you would think there are actually no points of inflection, which is interesting because this thing never equals 0. And but if you think about values of x, when x is like 0, this is like a negative number. But if x is 6, second derivative is positive. Interesting. So you can tell that I don't work these through in advance. So even sometimes I get confused. So here's a good example of what you would do if you're doing these on your own. I wonder what help me solve this problem. Does it pick up? Okay, it wants me to factor, which I did. I think it didn't like my notation. So I got this. All right. Note that there are cofactors and figures. Okay, that's what I did. X cannot be -2. X-intercepts, we said was, oh, since X cannot be -2, there's no X-intercept, which is what we said. And the y-intercept was -1/5, which is what we said. Check their simplification. Oh, I have the 0. Oh, I think it's -1/5. Y-intercept. All right, asymptotes. We said X equals 5. Horizontal, said Y equals 0. There's no oblique, I don't believe. All right. So the first derivative is -1 over X minus 5 quantity squared. That's what we said. Second derivative is 2 over X minus 5 quantity cubed. Oh, the domain. We can't have -2 or 5, so critical values where the first derivative equals 0. There are none. Oh, where is it not defined? It's not defined for X equals 5. That's a critical value, okay. Oh, -2 and 5, okay. Oh, where is it 0? There are none. Right, so there are no critical values, which I said. So 3 regions of, we said decreasing. Be that one. It's never going to be 0. Oh, undefined, sorry. 5. Same thing. No points of inflection. Next term of the graph, so there was so that's what I did. Either side of 5. That's what I did, and I said concave down from concave up from 5 to infinity. So I look at this graph. I've got one asymptote and a hole here, and I know it's concave down. It's got to be this one. All right, that was pretty tricky. So that was 25. I think we'll probably stop now. Let's see what the next question is. All right, we'll stop now and we'll continue on with the next video.